At last, it can be told. Yes, this is Mick McQuaid here with the second of today's 4 videos. And in this video, I'm going to reveal the answer to the question we were all asking during the last video. Why is this MSE curve U-shaped? And the short answer is that it's composed of 2 curves, each one of which forms part of the U. The long, painful answer, though, is what we're going to look at right now, and that is this equation. What is it? Equation 2.7 in the textbook. And this equation it will reveal to us something called the Bias-Variance Tradeoff. So this equation takes the expected test MSE, so the expression on the left-hand side is what's called the expected test MSE. And the expression on the right-hand side is that expected test MSE decomposed into 3 parts. And somewhere in here it says, it can be shown that this equals this, and we're not going to make you do that. So that's part of the whole non-mathematical nature of this course in comparison with other machine learning courses. What would be typical in a more advanced course would be that you would have to prove that this equality holds. But in this class, we're simply going to take it as a given that this equality holds. You don't have to do it as an exercise. And we're going to exploit the meaning of this to figure out a very important trade-off that we have to make when we're deciding what the best machine is to use. So that trade-off is the trade-off between variance and bias. So the way it works is this. The expected test MSE, by the way, this is different from the training MSE. So previously, we looked at training data, and we got an estimated training MSE from the training data. Then we make our prediction, and then we have some expectation about what's going to happen when we see the test data, and that's what this is. What is the expected test MSE? What's going to happen after we get this hitherto unseen test data? The MSE is going to be composed of 3 parts, and we would love to be able to minimize them. Now, one of these 3 parts we don't have a hope of minimizing. Can you guess which one that is? Take a second and place your bets. Okay, you've placed your bets, and you were correct if you bet that we don't have a hope of minimizing the variance of epsilon. That's the random part, that's the unexplained error term. That's the error term where we might get lucky. We might have a low amount of variance. In the reality may be that there's a low amount of variance, and it'll make it easier for us to make a prediction. But we can't control that. But what we can control is the variance of our model and the bias of our model. See, these are both based on the model that we form, or the machine that we form. And so we have to understand these 2 concepts that are mentioned here, low variance and low bias. We have to figure out what we mean by variance, what we mean by bias. Now, we've already looked a little bit at variance. We said that the more flexible, yesterday we looked at 2 pictures, 2.9 and 2.10, and oops, I forgot to look at 2.11. Let me I'll go back to that in a second, but we saw that the more flexible models suffered from the fact that there was greater variability if they were going to be rerun from training data to test data. A more flexible model suffered, particularly if there was high variance. If this was a large number, the more flexible models suffered from that. The less flexible model didn't suffer so much from that. But the less flexible model is also a simpler model. And a simpler model introduces bias. So the intuition here is simply that that reality is complicated. And a really simple model, although it may be pretty good, is missing something. And that, what it's missing, we'll call bias. So this is a penalty, in a sense. See, what we want to do is minimize this number. So the larger these numbers get, the worse off we are. So this is kind of a penalty for simplicity. And this is kind of a penalty for flexibility. But this penalty for flexibility applies mainly if this is large. the penalty for flexibility is not as great if this is small. Okay, I hope that makes sense. Let's go back to this example here that I didn't show last time. And this is a case where the variance of epsilon is small. That's what this dashed line here is, the variance of epsilon. So what we have is this very simplistic linear regression model that performs terribly on both the training data, that's the gray line here, and the test data. This overly simplistic thing isn't ever going to be good. There's very little variability, so remember that the black line, here I'll zoom in because I can't even see which one is the black line. Okay, so this black line is the reality that we're pretending we don't know about. The little circles are what we've simulated from reality, and the blue and green lines are both splines that we're fitting to this to the simulated data, as well as the regression line. And both of these splines are always going to be better. They're always going to be better in part because there's low variability, and also because they're less biased because they're more complicated. So we have the simplicity penalty operating here against linear regression, but we don't have very much of the variance penalty applying here. We had a lot of the variance penalty applying here, and we had a lot of the variance penalty applying here. So that's the reason that we got this U shape was we have a reduction in the MSE that we're able to attain because of a decrease in bias as we get more complicated. But then we start to lose that advantage as we get even more complicated because of the increase in variance. Okay, so let's go back to this curve that brings all of that together, or this diagram, I should say, this picture that brings all of that stuff together, and that's this picture right here. So this picture summarizes 2.9, 2.10, and 2.11 in terms of MSE and flexibility and the components of MSE. So this is a component of MSE, this is the variance of epsilon, this is a component of MSE, this is the squared bias, and this is a component of MSE, which is which is variance of the model. So each of these three things, this dashed line, this blue line, and this orange line, each of these three lines is contributing to push this up. Okay, so we get this U shape from figure 2.9. In this case, we have, in the case of figure 2.10, the reality is such that the bias is never really high. The bias isn't really a big problem here. The variance of the model is a big problem in the case of the more flexible models. I guess this was the one where regression performed the best. And then in this one, we have a tremendous bias penalty and a tremendous reduction in bias as we increase flexibility, but we don't have much of an increase in the variance penalty. The variance penalty isn't great, and the reason the variance penalty isn't great is because we just got lucky. The variance of epsilon was small here. That's an external thing that we can't control. If the variability of epsilon is low, then we're in good shape. We can make better predictions. It's always going to be the case that if the variance of epsilon is low, we can make better predictions. That's just a question of luck. Okay, so that's really the story. That's really the whole story, is that there is a trade-off between bias and variance of the model, and that a simple model tends to be more biased, and a flexible model tends to have more variance. And depending on the situation, by the way, this vertical dashed line is the optimal location. This is where the sums, the sums of these two, or actually I guess the sums of these three are the lowest. You only have control over these two, but this is where the sums of these three are the lowest. This is the desirable amount of flexibility. So what you can see from this, hopefully the big takeaway here, is that the amount of desired flexibility varies in different circumstances. It varies based on reality, and it varies based not only on the shape of reality, but also the variability of reality. So this is the case where we would like the least amount of flexibility. Here's the case where we would like the medium amount of flexibility. And here's the case where we would like the most flexibility of these three examples. And that's that. That's the end of the second of our 4 videos, the bias-variance trade-off. Next, we're going to talk about the classification setting, plus possibly a couple of things that I missed. Let me just take a quick look at this. Yeah, so classification is going to be a bit longer. There are quite a number of things to talk about here, quite a number of concepts to talk about here. And then the 4th video will be about exercise 2.4.9, which is going to require talking a little bit about R. So thank you for your attention.